Hello, my name is Nicholas Clark.
My name is Seongwon.
Hey, my name is Zack, and we're under Coach Sean Faruzian at Miracosta College, here to present on Problem C, Modeling Social Media Content Moderation Techniques. Here's a brief introduction to the layout of our presentation. We'll begin with an overview of the goals and research that we established to build our models, and we'll dive into the model itself, discussing its assumptions, conditions, and coefficients. To assess the models, we'll then look at the results, especially qualitative analysis, the effect of changing the coefficients, and of course, how to interpret the results. To conclude, we'll answer the golden question: what does our model show? How effective are these content moderation techniques? And how accurately can we determine that? Which leads us into our overview. We have two main goals. We want to create a model that represents the situation as accurately as possible, which boils down to figuring out which content moderation technique is most effective at preventing misinformation. To guide these conclusions, we found a solid body of research that supports the following. In essence, it's proven that flagging posts is not an effective way to stop the spread of misinformation, and that censoring is much more reliable. Other key takeaways deal with the severity of the spread of misinformation, which will be discussed later in the presentation. With that in mind, we should briefly introduce the inspiration for our model, which is the SIR model. This equation is typically used to model the spread of disease in an epidemic, but in this case, we're going to use it to model the spread of information over time on social media. Normally, S is the population of the susceptible unexposed patients, I is the population of those infected, and R is of those exposed and then recovered. Of course, there's movement between each group, meaning S can travel to I and I can travel to R, and there's coefficients to illustrate this. Beta is the effective transmission rate between the S and I, and gamma is the recovery rate between I and R. So this SIR model gives us a really strong foundation upon which we can build our assumptions and eventually our models. And I'll leave that part to Seongwon.
The first assumption we made in our mathematical model is that the population for the model is closed, which indicates that there are neither new users nor members leaving the social media platform. Based on the SIR model, our model consists of three social groups as functions of time: ST for the number of uninformed social media users, IT as the number of misinformed individuals, and RT as the number of correctly informed individuals. Here, we assume that the population of ST can go to either IT or RT, but not vice versa. Because you can't return to being uninformed once you have seen the information. Also, the population from I can move to R, and R can move to I. We assume that all interactions between social groups are one-on-one, and no social media users stay neutral. This implies that eventually the population of S will become zero, and it will be transmitted to either I or R. As you assume that the population is closed in our model, the sum of the rate of change for each compartment, S, I, and R, is zero. Our model focuses on examining the rate of change for the uninformed, misinformed, and correctly informed groups with respect to T. With coefficient of being the probability of S individuals moving to I per unit time, and coefficient B being the probability of S individuals moving to R per unit time, our model has ds dt equaling negative ASI minus BSR. We added two more constants, C and D, each representing the probability of I population moving to R per unit time, and the probability of R population moving to R per unit time. Accordingly, we have set di dt to equal as ASI plus d minus CIR. The ASI comes from the population pulled from S to I, and d minus CIR describes the exchange between I and R. Similarly, for dr dt, we set it equal to BSR plus d minus DIR, the difference between being that BSR describes the population pulled from ST to RT, and C minus DIR is the negative version of the term seen in di dt.
We then move on to the predictions of our model. To start, we define a variable alpha equals d minus c as our misinformation coefficient. This measures how effective the content moderation is relative to the misinformation. We then split this into three cases: one where alpha is greater than 0, one where alpha is less than 0, and one where alpha equals 0. In case 1, this means that d is greater than c, so there will be more movement from R to I. which in turn causes more individuals to switch from the correctly informed group to the misinformed. In case 2, we see the reverse, where C is now greater than D, which means that there will be more movement from I to R, leading to more people moving from the misinformed group to the correctly informed. Lastly, in case 3, we see a situation where D and Z are equal, so this means that there is equal movement between I and R. The next prediction is that involves the coefficients A and B, which describe the flow from S to I and S to R respectively. We split this interaction into 3 cases, with the assumption that the initial populations of I and R are equal, shown as S of 0 is equal to R of 0. In case 1, A is greater than B, which means that there will be increased movement from S to I. In case 2, A is less than B, which means that there will be increased movement from S to R. And finally, in case 3, A and B are equal, which means that there are equal amounts of people going from S to I and S to R. The interaction between these coefficients show how effective the content moderation is before an individual is exposed to misinformation and when users are first being exposed. Next, we move on to our qualitative analysis. And the first one we did was on flagging posts. According to an MIT study, false news is 70% more likely to be shared online than the truth. And the initial speed of misinformation, the initial spread of misinformation could be 6 times higher than the truth. Another study found that flagging posts didn't affect the spread of misinformation, as individuals were less likely to believe the truth once they'd already been exposed to misinformation multiple times, which we refer to as repeated exposure, and that misinformation is easier to believe than the truth. Using this research, we concluded that the coefficients would change accordingly. A would increase while B would decrease, which predicts more movement from S to I than S to R, leading to more people initially choosing to believe the misinformation rather than the truth. We also concluded that C would decrease while D would increase, which shows more movement from R to I than I to R, leading to an increase of people moving from the correctly informed group to the misinformed after they had already chosen a side. Next, we move on to the qualitative analysis of censoring. According to a study done by researchers at Yale and Boston University, censorship can be effective at stopping misinformation early and not allowing it to be viewed by multiple people. In turn, it stops repeated exposure to misinformation and allows the spread of the truth to catch up to the misinformation, which we established earlier as being inherently faster than the truth. In our qualitative analysis, we interpreted this as a few coefficient changes. In this case, A would decrease and B would increase, which means that there will be increased movement from S to R than S to I. This interaction shows more people believing the truth rather than misinformation initially. C would also increase while D would decrease, which results in more movement from I to R than R to I. This shows that there's an increase in people believing the truth over the misinformation after they had already chosen a side.
Now that we've done some qualitative analysis on both the content moderation techniques, a couple of things have become pretty clear about their effectiveness. Like Nick mentioned, when using flagging posts, IFT eclipses RT, meaning there's a faster transmission of misinformation than fact, leaving more people misinformed than properly informed. On the other hand, when censoring is used, there's a much slower transmission of misinformation. Eventually, RT eclipses IFT, meaning that there are more informed people than misinformed ones. The conclusion is clear, and it agrees with both the research and our models. Censoring is a much more effective content moderation technique than flagging posts. But of course, we should ask, how valid are these models? So let's take a look at the strengths and weaknesses. The model's limitations lie mostly in the assumptions that we made. First, we have a closed population, which in a digital space like Twitter is not realistic with an acceptable error. Secondly, we assume that the uninformed population S of T goes to 0, meaning nobody stays neutral and all individuals become either misinformed or properly informed. That being said, the strengths of the models definitely outweigh these limitations. First of all, the coefficients we included allow for more dynamic population flow than a pure SIR model. Instead of only observing each population as a whole, we can see the nuanced flow of individuals between groups that we otherwise couldn't. Additionally, finding data that discusses each individual tweet about a subject is not easy to get, but this model solves that problem. How? Well, our results studied the ratio of populations, which is also a lot easier to interpret. That being said, in an ideal world, we would have access to as much data as we need. We could account for all the minutiae of something as intricate as information flowing in a social network. A better model isn't impossible, it just requires more study, which is the next step in our process of modeling the effectiveness of content moderation techniques using differential equations. Here's our references and sources that we discussed throughout the presentation, and thank you so much for taking the time to watch.